we're going to wrap things up in this last lecture about point group theory and symmetry. So there's one last thing left for us to do, and that is to determine which symmetry patterns of the character tables give rise to the iron-Raman bands. And for that we have to learn how to come up with a reducible representation. So the character table are the irreducible representations. Those symmetry patterns are referred to as irreducible representations. And so we'll do this in a minute. Just as a summary here, if we have a simple molecule that's nonlinear, there are going to be 3 times n total motions. 3 are translations, 3 are vibrations, 3 are translations, and 3 are rotations. And then if you subtract that out, that's the number 6 here, we get 3 vibrations, which are the iron-Raman bands. And so they're shown here. We have symmetrical stretching, anti-symmetrical stretching, and bending. And so those are the only ways that these molecules, this particular molecule, can move in one space. All right, and so in order to assign or come up with that reducible representation, we need to assign 3 vectors to each atom of the molecule. All right, so each atom here gets a set of vectors x, y, and z. Okay, anyway, it looks pretty sloppy, but you get the idea. Let's focus on a single atom to go through this. So you follow these rules, and this is different from what we did when we came up with the character table. So those sets of rules are different. First of all, it's easier because any atom that moves gets a 0 value, which for water, these two are moving when you do a C2, right? So we don't worry about those 6 vectors. We only worry about the 3 vectors that are on the axes in this case. Or if you have a mirror plane, you only worry about atoms that are on that mirror plane. Or an inversion center, even easier. You just worry about that single atom, if there is one, on the inversion center, because everything else moves, right? So that's convenient. So we don't have to worry about, so first of all, we have 9 vectors in this case. And we for the C2 operation, we only have to worry about the 1 set of vectors. All right, so let's take a look at what we do if the atom stays put and just rotates or reflects or inverts. So the vectors that do not move get a positive value, right? So here we're going to do the C2, this is our example, through the z-axis, right? So the z-axis is on the axis of rotation, so it just moves. It just still points in the same direction. So it gets a +1 value. And the other 2 vectors, they rotate into opposite directions, right? So vectors that go in the opposite direction get a -2 value. So this one gets a -1 and a -1. So here the y and the x are the 2 that get rotated. Okay, so let's just apply that to the water molecule. So if I ask you to do that on a quiz or an exam, you will have to look at the character table. You'll have access to that. And first of all, if I give you water, you have to determine the point group, of course. So it's the C2V point group. Then you write down all of the symmetry operation. You obtain them from the character table, and you assign a set of vectors to each atom, and then we apply all of those operations one by one and come up with that reducible representation here, represented this symbol R reducible. So if we do an E, nothing moves, all 9 vectors have a value of 1, so you get a 9. Pretty simple. No atoms move, all vectors stay put. Every single vector gets a +1 value. We already did the C2, 2 atoms move, and so we end up with a -1 character for the reducible representation. So again, it's just like what we looked at. We have a single atom, and 2 of them are moving, 1 of them stay put. So if you add all this up, you come up with an overall -1 value. Now, for the 2 mirror planes, we need to distinguish between the xz and the yz. Now, the xz plane is the one that goes through here, but not through the hydrogen atoms, right? So it just cuts through here. I have a hard time with it today, but it's the one that comes right at us and goes through. So the two hydrogens are moving, and there are only there's only one atom on this plane, and there are two vectors on the plane, and the two vectors that are on the plane are the x and the z vectors, right? Because that's the xz plane, so the xz vectors are on it. So they stay put. They each get a +1 value, and the other one gets a -1. So we end up with a +1 for this vector. Okay, did some magic here. Erase some of the clutter so we can move on to the next one. We have 9, -1, and +1. Now the YZ is the one that's in the plane of the board. So now we have all three atoms that are on the plane, and they stay put, so we need to look at them. But the good news is that each atom on the plane gives rise to the same overall character, which is +1. Because for any plane, there are two vectors that are on the plane, and the other one is perpendicular. So those vectors that are on the plane all get a +1, and then the other three that are perpendicular to the mirror plane, they get a -1 value. So we end up with an overall -3 character for that. So this is our reducible representation for the C2V for water in particular. Now, as a summary here, we're going to keep things pretty simple. So threefold x's and things like that are going to be pretty impossible at this level to do. We're going to keep things simple. So we're going to look at like a CS or a C1 or a C2V or a C2H. So that limits it, limits to what I can test you on, right? So but just as a summary, so the two types of things that you are going to have to worry about are mirror planes or twofold axes. And so every time you have an atom on a mirror plane, you're going to end up with a +1 overall value. Okay, and every time you have a C2, an atom on a C2, you're going to end up with a -1 value. So that's a rule of thumb if you have a hard time visualizing that. But if you have a plane and an atom is on that plane, there are always going to be two vectors that are in the plane and then another one perpendicular. So that's how you get that +1 overall character. And so with the same idea, if you have an atom that's where all vectors are rotating, two of them are going to be perpendicular to this. They will rotate here in red, right? And then one is always going to be along the axis, whether it's the Y or the Z. See, I've chosen the Y here just to show you it doesn't matter. And of course, if we assign it here, if the C2 is this way, then we are also going to end up with a -1 value. Okay, so what do we do with that? So step one, of course, is to come up with the reducible representation, which we just did, and then after that we're going to do a summation. Now the summation over here, so what you want to do is you want to look up your character table for that point group of the molecule, and you want to put the reducible representation on top, and we will apply this summation here. So H is the number of operations, and the number of operations you determine by just looking at the point group table. So we have 1, 2, 3, 4 operations, so H is equal to 4. So it's 1 divided by 4. And we do this for each of the symmetry patterns. We'll do this for the A1, the A2, the B1, and the B2. So let's just do the A1 as an example. So the summation is chi R times chi I times N. Now chi is the character, R stands for reducible representation. So the character of the reducible representation, which is 9, times the character of the irreducible representation here, right, which is 1, times N, which is the number of operations. And the number of operations for E is 1. There's only one E. In fact, it's N for every single operation. So there's only one C2, there's only one sigma V in the XZ direction and one sigma V in the YZ direction. So that makes that easy. N is always going to be equal for 1 in this case. Sometimes you do have multiple of the same. If you multiple C3s, we've seen that. And then you would multiply. So instead of going 9 times 1 times 1, you would then have 9 times 1 times however many operations there are. So that's our sum 1. Then we go to the second one, which is the C2. So we take minus 1 times 1. So I'm going to put this in parentheses. Minus 1 times 1 times 1. Let me make it like this so we can see each of the summations. And then it's 1 times 1 times 1. And then the next one is 3 times 1 times 1. So 3 times 1 times 1. And when we add all that up and we divide it by 4, so we have here 9 minus 1 plus 1, plus 3 gives me 12 divided by 4, which is 3 A1s. And then we just do that same thing for each of these operations, and we come up with the total number of symmetry patterns. And the total number of symmetry patterns is going to be equal to 9, because we have 9, we have 3 translations, 3 rotations, and 3 vibrations. See where I'm going with this? So let's do one more. Let's go move on to the A2, and then I think that's enough for this example. But if we're going to do the A1 summation now, we have 1 over h, which is still 1 divided by 4, and then we do the character of the reducible representation times the character of the irreducible representation times n, which is always equal to 1. So here I need to, n is equal to 1 and h is equal to 4. So my h's and n's sometimes look like 1, so I need to be careful. But anyway, so it's 9 times 1 times 1, which is 9. Then we have minus 1 times 1 times 1, which is minus 1. Then 1 minus 1 minus 1, which is also minus 1, and then 3 times negative 1 times 1, which is negative 3. So that ends up being 4. So 9 minus 5 equals 4. So 4 divided by 4 gives me 1A2, and that is that. So here I have the summary of all 4. I highly encourage you to go through this by yourself, to do the B1 and the B2. And also note that my summation here, I have simply left out n here. This should be 9 times 1 times 1. So I've left this n out here for every single one of those additions. And so we end up with 3 A1s, 2 A2s, 2 B1s, and 3 B2s. And so those are then, this is the total number of motions for the water molecule in the C2V symmetry. And so the next thing is we're going to take out the translations and the rotations. We can find them from the character table. The translations are going to be here. See, I have a Z, that's my A1. And I have the X and I have the Y. So we have a B1 and a B2. Those are my 3 translations. The rotations, I find the RY and the RZ. And so they are next to the irreducible representation Mulliken symbol here. So we have an A2 and a B1 and a B2. So then I go back and I subtract those out from what we just determined, right? So we'll take the A1 out from here, end up with 2 A1s. We'll take the A2 out, so that drops out completely. The 2 B1s drop out, and then 2 of the B3s, and so we end up with 2 A1s and 2 B2s for the total number of vibrations. And then the last question I'll ask you is to which ones are IR and Raman active, and so any symmetry or any Mulliken symbol or that has something next to it. So in this case here, if you look at the Raman and IR bands, right, so IR and Raman, it's that so what did we have here? We had A1s and B2s. So we had A1s and B2s. And so as long as there's a character in that column, whether that's a Y or an RZ, they're going to be IR active, and the same is true here. So every single band in this case is IR and Raman active for this point group. So these all are. Answer is easy. They all are IR and Raman active. Let's look at one last example and then put a check mark on the symmetry. We have a different molecule here. This one has 4 atoms, so we know that 4 times 3 will give us a total of 12 motions. 3 translations, 3 rotations. We subtract them out, so this time we're going to end up with 6 vibrations. So that's what we're going to determine the symmetry patterns for those 6. And so the point group is a C2H. We have a horizontal mirror plane and an inversion center, and a C2 that goes through here. Pretty simple. And so we set up the reducible representations. Each atom has 3 vectors, so this time we end up with a total of 12 vectors. So for the E, we have a total character of 12, right? All vectors stay put. The C2, so all atoms move. And I didn't say this, but yeah, sure, they reflect into each other, but as long as they're moving, we don't worry about it. So we only worry about atoms that are on the symmetry element, which means they are on and move with the symmetry or are reflected through that. That makes that C2 character pretty simple because all atoms move, so every vector gets a value of 0, and the same is true for the inversion center, which is also in between atoms and not on an atom. So again, we get a 0, but then when we get to the horizontal mirror plane, every single atom is on that mirror plane. And as I said a minute ago, we have for each atom, we're going to have 3 vectors, 2 of which are going to be in the plane, and the other one is going to come at us and then reflect in a different direction. So we end up with a +1 value for each atom. And since we have 4, that is the total number of 4. So that's really, once you have that, the rest is just a simple summation. You just have to pay attention to the summation and not do what I do, take 12 divided by 4 and come up with the wrong number. And anyway, let's just do one example and then you are on your own, right? So we're going to do the AG. For the AG, again, we're going to do the character of the reducible representation, which is 12, times the character of the irreducible representation, which is 1, times the number of operations, which is 1. Of course, I forgot the 1 over H, which is 4, right? We still have 4 symmetry operations for the C2H point group here. 1, 2, 3, 4, and N is equal to 1 for each of the symmetry elements because there's just one inversion center, 1 horizontal plane, 1 identity, etc. Okay, so we have the first one is 12. The next one is 0, pretty easy because 0 times 1 times 1 equals 0. And then again we have a 0 here, plus 0, and then 4 times 1 times 1 is 4. So we end up with 16. And 16 divided by 4 gives us 4 AGs. And so you just go through the tedious motion of doing that for each of them. You end up with 4 AGs, 2 BGs, 2 AUs, and 4 B4s. We do the same thing again. You go to the character table and subtract out. And I'll go back real quick. Again, if you're looking for the rotations, it's going to be an AG and 2 BGs. If you're looking for the translations, it's going to be the AUs and the BUs. And then at the end of the day, if you have any of the BUs or AUs that are going to be the vibrations, then they are only IR active, right? Because this is IR and this is Raman. So this is an example of where IR is more useful than Raman. You will not see these bands in Raman, right? Once you subtract out all of the translations and rotations, you end up with 6 total vibrations. That's another one little thing you can do. You can add those up, and since we know we need to have 6 vibrations, if you have this, most likely you did it correctly. And then what the AGs are also IR active because there's a character in that column next to each of the symmetry patterns, but the AGs are the only ones that are Raman active. The AUs and the BUs are both IR. They're only IR active. So that's the end of this lecture. And next is coordination chemistry.